We're going to finish section 1 today, and the college syllabus has these problems, so we're only going to do these. Save you guys some time. Page 436, and then a bunch of numbers that you need to do. So let's look at 115. Go ahead and erase that. So we have to read the big long combination thing. A common school locker combination lock is shown. The lock has a dial with 40 calibration marks numbered 0 through 39. A combination consists of 3 of these numbers. To open the lock, the following steps are taken. You turn the dial clockwise 2 full turns, and then you continue turning the dial clockwise until the first number of the combination, and then you reverse it and go counterclockwise 1 full turn, and then you continue turning until you hit the number, and then you turn around and go the other way and turn clockwise, you turn clockwise until you hit the third number, and then it should open. So the instructions are go around this way twice, and you go this way till you find the first number. Right. You just keep going till you find the first number. And then you go all the way backwards. No, so you go around once, one time, and then you continue going until you get to the second number. And then once you hit that, then you go backwards to the third number.
So is it like a normal lock?
Yeah, it's just a normal combination lock. Okay? So 15 says, given the initial position of the dial is at 0, how many degrees is the dial rotated in total if your combination is 35, 5, 20? Okay? So, no. So there are 40 marks. Okay? If there are 40 marks, what's the angle measure of each mark? So 360 divided by 40. So every number is 9 degrees. Yeah, the space in between the numbers is 9 degrees. Okay? So we have to follow these instructions. We have to go all the way around twice. So that would be 720 degrees. Does everybody get that? And now we're at 0, right? At 3. We start at 0. So we start here. Well, let's start here. And I go all the way around twice. And now I have to keep going until I get to 35. So it's going to be 720 plus 35 times 9 times 35, plus 35 times 9. Okay, so now I've reached the first number. What do I need to do? I'm just going to write it all out. Yeah. Well, it's just the total rotation. Rotations, in this case, are positive. So I need to go backwards a whole turn. So plus 360. And now I'm at 35, right? I'm right here at 35. And now I need to go backwards until I hit 5. How far is it from 35? Okay, so let me draw it out. So we do our 2 full turns, and we go all the way to 35, and then backwards a full turn, and backwards to 5. So that's 30. This distance is 30 times 9. So plus 30 times 9. And now the last step, I need to go straight to 20. 15 times 9. Good. $1,800. Somebody check. Is that right? Oh, where did we mess up? Okay, let's try again. So, so turn the dial 2 full turns. So that's 720 plus. So I go 1, 2, and then I go from 0 to 35. So that would be 1. Yeah, that's a distance of 35, right? So 35 times 9. Okay. Yeah. All right, so now we take this and we go backwards all the way to there, which is another 360. Yes. No, you're supposed to do one full term. So, oh, I know why. Well, no, the problem is we turned around again right here. So we go backwards, but we go this way to 5. And I wrote it the other way. So it's 10 degrees. Or so 10. So the blue is going this way. But the red, or sorry, the blue. No, that's right. We should turn around. So, yeah, that's right. So that's 2 rotations. And then you keep going to 35. Oh, yeah, you should. No, so that's right. 30 times 9. So 720 plus 35 times 9 plus 360 plus 30 times 9. And then we're here. And go back this way to 20, which is 15. No, we're off by a long ways. How many degrees is the dial rotated in total, sum of clockwise and counterclockwise, in opening the lock if the combination is 35, 5, and 20? So, wait a minute. 1800 minus... What was the answer? Look at that. Oh, yeah. They only have one full rotation. They counted this once. Well, either way, they messed up somewhere. I I think Cynthia's wrong. What do you guys think? Either she counted this as 360 or she didn't count that. Right, and then the third one says counterclockwise 1 full. So Cynthia is wrong. Yes, that's in degrees. 1800's in degrees. Okay, good. All right. 119. Yes. No, 1800 is correct, but the book said 1440. So we did it right. She missed 360 degrees somewhere. Curse you, Red Baron, Cynthia. Yeah, she's the modern Red Baron. All right, 119. if two humans are on opposite ends of the centrifuge, and or we're on 119, if two humans are on opposite ends of the centrifuge and their linear speed is 200 miles per hour, how fast is the arm rotating? Okay, this is the vomit machine. Okay, so we have this machine that it's a G-force machine to see how many G-forces you can handle. If you have too many G-forces, if you're sitting in a rocket and they shoot you straight up, all the blood is going to go to your feet and you'll pass out. Fighter pilots have a special suit they wear that compresses their skin, like it inflates with air, and it pushes on their legs and their arms to keep the blood in their brain. So, yeah, it's a problem. You can pass out pretty easily. Um, Machines can handle way more G-forces than people can. People don't do well under lots of G-force. We would be much better. That's true. Zombies would do well if it wasn't for the whole no brain and stink issue. So the diameter of this is 58 feet. Okay. And that's right at the bottom of the first column. Okay. And then the linear speed of the humans is 200 miles per hour. How fast is the arm rotating? So that would be an angular velocity, right? Okay. So this is 200 miles per hour, and it wants the answer in what? So radians per second. Well, at 200 miles per hour, how fast are we moving or how many feet per hour? So we want to change 200 miles per hour into feet per second, right? Oh, will that help? So how many feet are in a mile? 5,280 feet per mile. Okay, what else do I need to do? So there are 60 oops, that's upside down. So in 1 hour, there are 60 minutes. You could. And then in 1 minute, there are 60 seconds. And now, hours cancels hours, miles cancels miles, minutes cancels minutes. And I get 200 times 5280 divided by 60 divided by 60. Or sorry, times 5280. Oh, you're saying no to me.
Yeah.
I thought you were saying no to each other. Okay, what does that number tell me? Feet per second. So this little future astronaut is whipping around at 293.3 feet per second. Okay. So I want to figure out how many radians this person travels per second. So the Earth is moving something like 18.5 miles per second around the sun. 67,000 miles an hour. Yeah, no, it's not too big. Yeah. So we converted feet to or miles to feet. We converted hours to minutes, and we converted minutes to seconds. Yes, we need the circumference. Good. So circumference is either 2 pi r, or in this case, pi d. Pi d. So the circumference of this circle is just 58 pi, which is 182.2 feet. Okay. Well, let's think about this for a second. I want to know how many radians we are traveling per second. So right now I have the linear speed of how fast the person is moving, and I have the circumference. What can I do with those two values? I can find the number of rotations per second, right? So this is one rotation. Am I doing more than one rotation or less than one rotation every second? More, right? So how do I want to divide these? So I travel this far in 1 second, which is more than one rotation. So 293.3 divided by 182.2. What does that tell me? That's how many rotations per second. 1.6. So I now know we're doing 1.6 rotations per second. Now, boy, they are whipping around there, right? That's crazy. It's when your eyeballs start to flatten when you when uh-huh. So when Navy fighter pilots take off from an aircraft carrier, they they're they're bolted, literally bolted to the carrier, and then they turn their engine on full blast, and there's a little shear pin that connects them to the aircraft carrier. And once they're up to full power, then the guy pushes the button to launch it, and the launchers, which is steam, or some of the newer ones are electric, and the power hits that connection so hard that it breaks the bolt. So there's the wheel is attached to this plate, and this plate has a catapult on it, and there's a little bolt, there's a little thing right here, and it bolts them together, and then that bolt holds the airplane from taking off, and then when this catapult shoots, that bolt just shatters. And they hit so many G-forces that their eyes go dark because their eyeballs actually flatten. Well, I mean, it just, once the G-forces are gone, then it goes back to normal. So I've talked to some of those pilots before, and they say you make sure that you're not going like this because then your eyes flatten in a really weird way. If you turn your head, then your eyeball, they squish in a different way and you can't see anything. So the pilots are really good at just holding really still and pulling back on the stick. But yeah, a lot of we are not built for high G-forces. You know, it's just not good for us. Oh no. Well, I mean, when you throw a bouncy ball on the ground, it squishes and then it bounces back. Yeah. But it's, your eye is made of jelly, so we're fine. Okay. Okay, back to math. These astronauts are experiencing 1.6 rotations per second. Okay? So how many radians is 1.6 rotations? So it would be all the way around and then 60% more, right? So it's 2 pi plus 60% of 2 pi. You could. Yeah, that would work. No, they'll be about the same. Or we could just say 1.6 times 2 pi. That's just combining them into one. So that's actually easier than degrees. So, um, so 1.6 times 2 is 3.2 pi radians. So times that by pi. What does that mean? 10 radians per second. 10 radians per second. Now you remember that arm, you are 29 feet out, which is from me to the wall, right? And you're going to go around 1.6 times every second. That's way better than the gravitron at the carnival, right? Yeah, that's a terrible machine. Okay, and yes, full disclosure, I did puke out the side of the tilt-a-whirl at Lagoon once because they stopped me at the top, and my friend insisted on, you know, tilting, and so I actually had to throw up over to the right were the people in line, and so I leaned over him and threw up out the side. It was bad. My stomach can't take it. I wish I didn't. My thrill level is up here, but my nausea level is like way down here. So I have to do things like jump off bridges. Caitlin was there when I jumped off the bridge. Okay, 125. Sniffers outside a chemical munitions disposal site monitor the atmosphere surrounding the site. Shh. To detect any toxic gases in the event that there is an accidental release of toxic fumes. The data provided by the sniffers make it possible to determine both the distance d that the fume reach as well as the angle of spread that sweep out a circle sector. Yeah. They're not sniffer people, they're sniffer machines. Yes. talk about uh, talk about that really is a temporary job, isn't it? Yeah. Okay, 25. If the maximum angle of spread is 105 and the maximum distance at which the toxic fumes were detected was 9 miles from the site, find the area of the circular sector affected. So the wind must be blowing a little bit. So the gas is released here and it spreads 100 105 or 105 degrees for 9 miles. Okay? So if we go back to our area of a sector formula, which is on, it's at the bottom of 429, 1/2 r squared theta. So 1/2 times 9 squared times 105. But this has to be in radians. So we do 105 times pi over 180. So 105 divided by 180 is 7 pi over 12. So 1/2 times 81 times 7 pi over 12. So 1/2 times 81 times 7 times pi divided by 12 is 74, not miles. Square miles. Good. We're finding an area. 74 square miles. All right, 27. The structure of human DNA is a linear double helix formed by nucleotide base pairs that are stacked with spacing of 3.4 angstroms, which is a very tiny number, and each base pair is rotated 36 degrees with respect to the adjacent pair and has 10 base pairs per helical turn. The DNA of a virus or a bacterium, however, is a circular double helix with the structure varying among species. If the circular DNA of a virus has 10 twists or turns per cycle and an inner diameter of 4.5 nanometers, find the arc length between the consecutive twists of the DNA. So we have 10 twists. Okay, so each twist takes, if we do 360 degrees divided by 10, we have 36 degrees per twist. And the inner diameter is 4.5 nanometers. Find the arc length between the consecutive twists. So if the diameter is 4.5, then the radius would be 2.25. And each twist represents 36 degrees. 36 pi over 180 is 1/5, so pi over 5. I converted to radians. And then the arc length is simply the angle times the radius. So this would be 2.25 pi over 5. Yeah. 2.25, yeah, you'll want the decimal, because this is going to be in nanometers, right? 2.25 pi divided by 5 is 1.4 nanometers. That's the arc length, the inner arc length of one single twist. Yep. Yeah. Aren't you guys? That's for that particular virus. Yeah, they're all quite different. Yes. I'm a mutant. It's true. Yeah. The other me's a lot taller. Okay, 129. If the radius of a set of tires on a car is 15 inches and the tires rotate 180 degrees per second, how fast is the car traveling? Right. So in this problem, the radius is, well, I don't want to do it that way. So the radius is 15 inches. Okay. And the car is going to travel from here to here in 1 second. So the circumference is 2 pi times 15, or 30 pi. Oh. Oh, well, that's easy. They used the wrong formula. Piece of cake. Okay, 31. All right. 131. If the radius of a circle doubles, then the arc length doubles. If a radius of a circle becomes twice as big, then the arc length becomes twice as big. Okay, here's a trick. If you double a linear value, then every linear value will also double. Okay? But if you double a linear value, then the quadratic values will not double. They will go even larger. Okay, and so this is kind of just a good general thing to know. If you take a two-dimensional object, okay, and you stretch it linearly by double, every linear value in that direction will double. Okay, if I double it linearly, then the perimeter will double. Okay, perimeter maybe. Well, circumference is linear, right? So C is 2 pi r. So if I double r, then C will be twice as big. But area is pi r squared. If I double r, the area actually doubles and doubles, which would be quadruples. Okay? If you took a cube and you doubled every length, then it would be 2, 2, and 2, which would be 8 times larger. Okay? So whatever dimension you're in, doubling will double that dimension. But if you double a dimension and then you go to a higher dimension, then it would quadruple. Or if you did 3 in first dimension, then the area, the 2 dimensions, would be up by 9. Yeah, it would be 2 to the 4th. 16 times larger. And I don't know what you'd call that. You can't call it volume. It would be fourth dimensional volume or something like that. So in this case, we're doubling a linear value, and we're asking about a linear value, so it's true. Right. Now, if we said area, it won't double, it will quadruple. If we said volume, it wouldn't quadruple, it would octuple, or however you'd say that. Okay, 133. If the angular speed doubles, then the number of revolutions doubles. And we can do something really easy here. Let's say we do 1 rotation per second. If I double it, now I do 2 rotations per second. Oh, that was easy. Right, 4 pi radians. Yeah. So that one's really easy. They're both true. Okay. And 137 is the last one. Okay, we have this weird shape. So we have this one, and this one, and this one, and now, oh. So essentially, I have 1/4 of 4 circles, right? So the area of this one would be pi times 4 squared divided by 4, right? And the area of this one is pi times 3 squared divided by 4, and then pi times 2 squared divided by 4, and then pi times 1 squared divided by 4. So essentially, I have pi times 4 squared plus 3 squared plus 2 squared plus 1 squared all over 4, right? So pi times 16 plus 9 plus 4 plus 1, all divided by 4. 23 units squared. All right.